Hello everybody, so I'm here today to continue talking about our chapter of how do the derivatives affect the graphs and tell us about the graphs. Okay, so we're going to talk today first off about the second derivative test. So this is again a useful test to determine if a critical point is a local min or max. Now, one way that we can check that, of course, is the first derivative test. So remember that the first derivative test is where we just check what's happening to the sign of f prime. If f prime goes from a positive to a negative, then we know that it's going to be a local maximum. If f prime goes negative positive, we know it's a local min. But this isn't always the easiest thing to do, and sometimes it's a lot easier to justify the second derivative test. So basically, what the second derivative test tells us is if your first derivative equals 0, the second, that's crucial, the second derivative can tell us if we have a min or max. If we have a min or a maximum. Okay, and let me draw some pictures to show you how this helps. So if your first derivative equals 0 and your second derivative is positive, meaning of course that you're concave up. So let's see what that looks like. If you're concave up and you have a first derivative of 0, it is always going to be a relative minimum. Conversely, if the first derivative equals 0 and the second derivative is greater than 0, meaning, less than 0, meaning that you are concave down, then that means, okay, you're concave down, slope of 0, that means you have a relative maximum at that point. So as long as the first derivative is 0, you just find the second derivative at that point. So let me give an example. So suppose I tell you that f equals 2x cubed minus 15x squared minus 36x plus 1, and I say to find all x values with a relative min or max. An astute student might point out we did this exact same problem using the first derivative test, but today we're going to use the second derivative test. So first off, we're going to find where f prime is 0. So we're going to find those critical points. And then at each one, we're going to find the second derivative and see if it's positive or negative. Okay, so let's go ahead and do that then. My first derivative here, of course, is 6x squared minus 30x minus 36. You factor out a 6, you're left with x minus 6 times x plus 1. So your critical points happen at x equals 6 and x equals negative 1. Now, instead of making a sine line graph, which of course you could do, in this case, you can't always do it, but in this case, what we're going to do is after we have these two critical points, we're just going to find f prime at each one. So at x equals 6, now my f double prime is 12x minus 30. So at x equals 6, my first derivative of 6 equals 0. My second derivative of 6 is equal to 12 times 6 minus 30, which is 42. Now, the answer doesn't matter. What matters is that second derivative is positive. So because we're concave up and have a slope of 0, that means that we have a local minimum at x equals 6. Okay, and then conversely, the other critical point, if we look at, say, x equals negative 1, your f double prime turns out to be negative 42. Again, the important part is that it's negative. So since my first derivative equals 0 and my second derivative is negative, concave down for slope of 0, so that tells you it is a local maximum. So that can be a useful way. Now, this is a case where we could have just used the first derivative test, but another example is like, say I just have a really wacky one that's like difficult to make a sine line graph, right? So I tell you that f prime of x equals x to the fifth minus 2x cubed plus 3x and then plus 2. And I ask you, does f have a relative min, max, or neither at x equals negative 1? Okay, so the two things that you want to find in this problem is you want to find f prime of negative 1 and show that to see if it's 0. If it's not 0, right, you know you don't have a min or max. And then we're going to find f double prime of negative 1. Now, making a sine line graph of this would be impossible. Like, we have no idea how to factor this. So because we don't have a sine line graph, that's an indication that we can use f double prime to kind of help us out at this point. So for example, f prime of negative 1 here is going to be negative 1 and then minus 2 times negative 1 minus 3 plus 2. Anyway, you see that that's 0. Okay, so the first derivative is 0, we probably have a local min or max. Turns out the second derivative is 0, it actually doesn't help. But let's go ahead and find this. So f double prime is 5x to the 4 minus 6x squared plus 3. So if I want to find f double prime of negative 1, I'm going to get 5 times 1 minus 6 times 1 plus 3, which is 2. Again, it doesn't actually matter what the number is. The important part is that f prime of negative 1 is 0. F double prime of negative 1 is bigger than 0. So we're concave up, slope is 0. So that tells us that we have a relative minimum at that point. So that's how the second derivative test can kind of be helpful, and we'll see some situations where this helps you out. Okay, the next thing that I wanted to look at was something totally different. I wanted to switch gears and talk about concavity and tangent lines. Okay, and this is something that I think you can see on yourself. Again, this is something I would never memorize, but this is a pattern that I think you can discover on your own. So I'm going to draw something that's concave up and concave down. Now on your paper, take a second and just draw tangent lines parallel to each one, or not parallel, but draw tangent lines for each of these curves at any points you want, and see if you notice. So one thing I want you to do is, if you see a bunch of tangent lines, on the concave up graph, aren't all the tangent lines below the curve? And in fact, that's going to be true no matter where you start. These tangent lines are below the curve. On the concave down graph, no matter where you draw them, any tangent line is going to be above the curve. So this is kind of a cute observation worth knowing, and occasionally you'll get asked a question about this. But again, it's not something I'd memorize, it's something I draw and try and do that way. Okay, the kind of question where this might come up is they might tell you that, like, suppose some function g has a tangent line at x equals 3 of y minus 5 equals 4 times x minus 3. Okay, and then if your second derivative is less than 0 for all x, is the tangent line above or below the graph of g? Okay, now in this case, like I just told you, right? I told you exactly what this is. We know just looking at it, I forgot to put a question mark, but we know just looking at this is a concave down graph. So the way you'd write this up is just say, okay, since that g double prime is negative for all x, okay, so that means you're concave down, any tangent line will be above the graph. So any tangent line is above the graph, or because it's above the graph, you might call it an overestimate. Okay, so those are some fun facts, the second derivative, and then talking about concavity and tangent lines. Thanks for watching, bringing some questions in class. I'll talk to you soon.